Welcome everybody to Lethal Language Models from Bitflip to RCE in Ollama. First, a bit about me. I'm Paul, and I'm a vulnerability researcher at Sonar, which you might know from our product Sonar Cube. I also like to play CTF with Team Fluxfingers. We also organize the online Hack Loose CTF, not the on-site one. And today we're going to talk about Ollama and how to hack it. And it all starts with Pwn2Own Berlin. And then I'm going to tell you about what is Ollama, in case you don't know. Then we're going to look at some bugs. And then we're going to try to exploit them. And finally, I'm going to wrap up with some disclosure and lessons learned. So Pwn2Own Berlin 2025. In case you don't know, Pwn2Own is a hacking competition. Basically, it's by Trend Micro, and they set out a set of targets. And in this edition, it's just software. And then people can have like 2 or 3 months to hack them, build an exploit, and then they can go on site and win money if the exploit works. And then it's disclosed to the vendors immediately after. This time it was at OffensiveCon, which is a very good fit because OffensiveCon is an offensive security conference. Pwn2Own is an offensive security competition. Very nice. And I was going to the conference anyway, so I was like, well, might as well take a look. And in this year, they added a new AI category. And first I was like, is this just marketing or is this something nice to look at? But actually, it's about the software that's used to run AI, LLM, or machine learning applications. And this is how the target category looks like. You might know some of these targets, for example, Redis, and you have different things also from NVIDIA. All of these are open source, which is not that usual for the competition. And there's also Ollama, which I decided to look at. Ollama is a tool to download and run LLMs locally. There's a public model registry where you can download popular models like Llama, DeepSeek, Gemma, and so on. And then you can run them locally. It's mostly written in Go, but it does use also some lower level code in C and C++, which mainly comes from the llama.cpp project. And this code is used to actually run the models for the inference. And yeah, it's low level code because it has to be efficient. If you want to use it, you first have to start your local server. You do Ollama serve in the command line, and then it starts listening on a port. And then you can use other clients to talk to it. For example, you use Ollama run, and then you just give the model name and tag. It's just like Docker. And then it downloads the model if it's not already downloaded. And then you get dropped into a prompt where you can then enter your input like in the normal ChatGPT website. For the architecture, we already seen the server and the client. The client can either be the Ollama run command or other client libraries or apps that talk to the server via the API. And for example, the client can tell the server, hey, please download this model for me. Then the server talks to the registry and downloads the model as a binary blob or multiple of them. And then these get saved to disk in a file format called GGUF. And then afterward, the client can tell the server, hey, please now generate a response for me with this model. And also, please, here's the prompt. Then the server spawns another sub-process, the runner. And this runner process then establishes an HTTP connection to the server. So these can send requests back and forth. Then the runner loads the model file from disk that was previously downloaded and then starts processing the prompt. And also the client can then send follow-up requests, which are then inferred in the same runner process. So it's reused for an amount of time. And when I learned about this, I was like, this model file looks interesting. Never heard of this file format. Let's take a closer look. And it's not very complicated. The file is split into different sections. First, you have a magic number and a version number. Then you have the count of tensors, which will come later in the file, and the count of metadata key-value pairs. Then comes the key-value metadata section. Here you have just stuff about the model, what architecture, what's the name of the model, and much more. Keys are always strings, and values can be strings, different sizes of numbers, booleans, and also arrays of those. And if you have an array, it's just an array of the same type. You cannot have an array with first a string and then a number. It's all the same. And you cannot have arrays of arrays. And then comes the tensor info section. In case you don't know what a tensor is, it's just a fancy way of saying multi-dimensional array. So this section holds then the information of how many dimensions and what are those dimensions of a tensor. And then the large majority of the file is just the raw data that basically is in these multi-dimensional arrays or tensors. So let's look at some bugs. And these are related to these files and the parsing of them. So I started to read the code. First I looked at the Go part of it, but then I realized that 1 year before me, researchers from Wiz also looked at it and they already found the juicy bugs, so they were all fixed. So I had to turn to the C++ code, and I got more lucky there. So the first bug I found is a textbook string copy bug. Here first a value is read from the model file as a string, and again we can tell Ollama, hey, please load this model from the registry, and we can also tell Ollama, load it from that other registry, please. Like with Docker, you can specify which registry to use. So essentially, as an attacker, we can control the model that is loaded. So we can also put any string into the metadata section, and we can make it big. And because it's a string copy, it doesn't do any size checks to check that the target buffer is big enough. And as it turns out, it is quite small. It's a fixed 32-byte buffer, so we just make a big string and it overwrites out of bounds. But I didn't find this bug very useful because at this point I was able to overwrite some pointers, but they weren't so interesting of how they were used. And also I didn't have an info leak, so I didn't know what I would overwrite these pointers with, so I moved on. Second bug, a type confusion. This is a helper function that is used to get a string item out of an array of strings from the model. So first, the code checks that the field that we're reading from is actually an array. This is good. Otherwise, we would treat, for example, a number as an array, which would be bad. But then they forget to check what the type of the elements inside the array is. So they expect it to be a string. That's why then at this point they read the ith element and treat it as a pointer to a string. But they did not check that this is actually what's in the file. So there could be numbers instead. And then they dereference a pointer from the GGUF string struct. So this would be an arbitrary controlled pointer dereference, a read. But again, I don't know what pointer I would write there, where I would want to read from. So I would kind of need an info leak to use this as another info leak. So also not that useful. So again, I moved on. And then I found the third bug. And this is a much nicer one. It's an out of bounds write. And it's not a linear one like the string copy. And it's on the heap. So what happens here is first, the block count is read as a number from the metadata and stored as the number of layers in the model. Then a vector is resized to have enough space for all of these layers. Then it's later used to set some values in this vector. But before that happens, there's another value that is read from the file, and this is an array of numbers. And these numbers are then used to index into the other vector. But as you can also see from the colors, these are completely distinct, and there's no check that the index is within the bounds of the pink vector. So this statement essentially, as an attacker, lets you tell the Ollama that, well, please set this element at this offset to true, and it can be entirely out of bounds, very large index, while the vector is very small. So I was like, oh, nice, I can set bytes right out of bounds. And in my interpretation, on the memory level, this looked like this. In pink, we have the vector storage area, and then as an attacker, we can control the offset, for example, this, and then it would write the value true, which I thought is just a single byte with the value 1 anywhere on the heap. And while this is better than the other bugs, I was like, I cannot really control the value that is being written. So can I actually do something with this? I heard other people in other talks do crazy things with like very limited primitives, but I'm not a pro binary exploiter. I only know my basics. So I was like, is this going to work out? But yeah, later I realized, yes, it might work out. So let's move on to exploitation. And for this, we first look back at, okay, what actually do we have here? What is happening? So the vector that we can write out of bounds, related to this, is a standard vector of type bool. And if we check the docs of this, then they say this is a possibly space-efficient specialization of the vector for type bool. And what this just means is bit packing. We have a vector of booleans, so we don't need to waste a full byte just to store one boolean. We can store one boolean in one bit. So for example, 16 elements, we just need 2 bytes. And then if we want to do something to the first item, we just do something to the first bit. Or if we want to do something at index 6, it's the 6th bit, and so on. So looking back at our bug, this basically gives us a bit setting primitive instead of just setting a full byte to the value 1. And this is much more powerful because now we can create arbitrary values in memory, but we can only flip zeros to ones, but not the other way around. Because again, the value that we write is never controlled, it's always true. But this is not too bad, because also if you think about this, if we have memory that is entirely 0, we can create an arbitrary value that we want there. But if there's memory that already holds a value, then we can only slightly modify it because we can only flip the 0 bits to ones. So now the question is, we know how to write, but where do we want to write? And so I just inspected the heap a bit and looked around what interesting structs there are. And there was the GGML backend struct. And this was interesting because it holds some values, but also includes another struct, an interface struct. And this includes a bunch of function pointers. And even more interestingly, some of them were null, which means this is all 0 memory. So at this field of the struct, we could create an arbitrary pointer. And also, very conveniently, there was code that would check if that pointer is null. If it's null, it's just ignored, but if not, it's called. And this code was also reached later in the inference. So if we overwrite the, for example, synchronize field and write an arbitrary pointer value there, it would later get called, which is a nice primitive to start your exploit with. And so I wanted to quickly verify that this indeed works. So I had to craft my own small model. First, I started out using just one that I downloaded from the registry, but those are a few gigabytes big. So this was quite annoying to debug because it always takes time to parse and bloats the memory and everything. So I spent a few hours or even days to craft a very minimal model that's only a few kilobytes. And that was hard because all of the parts of the model, all the dimensions, all the tensors have to perfectly fit together, because otherwise if you do, for example, a matrix multiplication to combine 2 vectors, which Ollama wants to do, then it might fail if the dimensions don't fit, and it would either abort because of a check or even crash because maybe there's more out-of-bounds reads or writes. And I didn't even want those crashes. I just wanted mine to work. And in the end, I got this. You have a block count of 1, so only 1 layer. So the vector is very small. And then down below, we have the indices array, which I wrote a helper function with that just generates all the indices that I need for this byte value to be written to that offset. And I ran it in the debugger, and very nice, we got the controlled jump to my arbitrary pointer. But of course, that's not enough. We need to know what to write in order to jump somewhere that is interesting for us and helps us to get a shell. So the next thing I did was to check the protections of the binary, or the security measures. And we can see that partial rel-row is enabled, which could help us later, but not directly. We have stack canaries. Stack is, of course, not executable. We are not in the 90s or in IoT anymore. But pi is enabled, position-independent code. And this means that not only the stack and shared objects are at random offsets in the process memory, but also the binary itself. And this essentially means we don't know any memory section that we could jump to because we don't know any of these offsets. So we would need an info leak to then know what to write and to move on. But there comes another problem. If we look back at the architecture, the the server spawns a new runner process to host and execute the model when the client tells the server to do this. And this process, every time a new process is spawned, gets a new memory layout because it's not a fork. If the server would just fork, then the memory layout would be inherited, but it's always an entirely new process. And for each new unique model file, every time a new process is spawned. So I have to write the offset that I want to write or the pointer that I want to write into the model and then load it. But every time I do this, I get a new process where I don't know anything about the memory layout. So it's kind of a chicken and egg problem. And even if I would have a memory leak in the runner, it would only be executed after the model loading, and also before the model loading, I cannot interact with the runner process, only afterward. So this was kind of a deal breaker. And actually at that point, I was like, is this actually exploitable? Or maybe not for me, maybe others could. But so I put Ponto on aside for the time being. I also had other things to do in life. But later, I still came back and wanted to exploit this because I thought like this bit setting primitive is kind of interesting. The struct fits very nicely also with this convenience function that calls or doesn't call a null pointer, and so on. So I went back and I was like, okay, I will just turn off pi and see if I can exploit it without it. And then maybe later I learned more and maybe I can do more. So let's do this. And also, yeah, by the way, this is Go's default. If you just build a Go binary with Go build, pi is not enabled. I'm not sure why. Maybe performance. I don't know. But for Ollama, they explicitly enabled it for their release builds. So the new exploit plan is where to write. We already know this into the GGML backend struct to override some function pointers. But what to write? Now that I turned off pi, I do know the addresses of all the functions, all the code from the binary itself, still not from the stack or from libc or something like this, but since it's a static binary, there's a lot of code there, so this could be helpful. So first I checked for a one gadget, which would be just a single address I need to jump to, and then it gives me a shell. But there was none, and this would be useless because we're not really directly talking to standard in, standard out of the runner process. It's like two indirections of HTTP APIs of how we talk to it, so yeah, would be useless anyway. So good old rob chain was the next idea, and that's what I did. So if we look at the CPU registers at the point where the arbitrary pointer is called, we can see RAX holds the pointer that is being called, and RBX and RDI hold pointers to the very GGML backend struct that we already wrote into. So it would be very nice if this could become our new stack, because for a rob chain, you need to control return addresses on the stack. But since we don't write on the stack yet, maybe we can make something else, our stack, where we can write into. And I looked for such a gadget, and very nicely, there was one of them. It moves RBX into the RSP register, which just makes it the new stack. And then the stack looks like this. The gadget then pops something from the stack, which is very, very convenient because the first thing in the GGML backend struct is a pointer to the GUID. So it's a pointer to a read-only section. And since we can only flip zeros to ones and not the other way around, we wouldn't be able to make this pointer that's already there a valid pointer to a code section. So without this pop RBP instruction, everything would crash, but it all played out nicely, and we can put more gadgets. But there's more non-zero memory in the struct. There's more function pointers. So the first one is a pointer to the GGML backend getName function. And while this doesn't do a lot, it doesn't take an argument, it just returns a pointer to a string. Later in the struct, there's other functions, and those might crash if they're executed the wrong way, if the arguments don't fit, or they would also probably clobber some CPU registers, and this would mess with our rob chain. So I looked at the address more closely and checked which bits are 0 and 1. And it turns out you can flip these 3 0 bits to 1, and then it becomes an address of a return instruction. So this is very nice because this is a no operation in a rob chain. And so I extended my script that this memory is also slightly altered. And then this is the rest of the ROP chain, and now we're going to walk through it. Oh, sorry, this is first how the rest of it looks like. You can see there's more addresses to functions. And also in red, we have the initial gadget, so we cannot change this entry, but we can change the others. So this is the ROP chain, and we will quickly walk through. First, we pop RDI from the new stack, which is the address of the global offset table entry for free. So the global offset table is a section that holds addresses to functions in shared objects, so third-party libraries. So for example, for free, it's coming from libc, and when the program loads, the program doesn't know where libc will be because it's at a random offset. So the loader will write the address of free into this table, or the program will do it lazily, and then later it knows where to call. So we will need this later. We now have the address of this entry. Then we also pop the distance between the free function and the system function into another register. And we also skip the initial pivot gadget by just popping it into another register, but not using it as a return address, not jumping there. Then I turn two more of the existing functions into return gadgets, just to skip them. And then we have the interesting gadget, which is adding a number to this GOT entry. And what this essentially does is, first there's the address of free, so the GOT entry points to the free function in libc, and then we add the offset that we calculated, and now the free entry points to system, which is convenient because both free and system receive a single argument, which is a pointer. So if now after this we can make Ollama free a controlled string, it gets actually executed as a system command. Now I skip two more of the existing function addresses, and then I need the final gadget, because in Ollama, model inference is done multi-threaded, and so there's a main thread that's waiting for the worker threads to finish, and I need to gracefully make this thread finish, otherwise it might crash later, because we're not on a real stack. If it continued to return and try to move on with the stack, it would crash. So we simply tell the OS, hey, this thread is done, you can get rid of it, and then eventually the main thread notices this and will see, oh, all the work is done, let me move on. So at this point, to recap, we have overwritten the GOT entry of free with the system, so the next time free is called, actually system is called. So how can we make sure that this is called with a controlled string? I looked into the Go code, and from there sometimes they even call into C functions because they have to interface with the C code. And here we can see that a part of our prompt, the text variable, is actually turned into a C string, and then later it is freed. So we can either in our initial prompt just put our command that we want to execute, or after this first thing ran, we can send another prompt and then our payload triggers. That's where it is. And all you have to do is send a follow-up completion API request to the server, which forwards it to the runner, and then eventually our command is executed. So let's see if we can demo this. I prepared a little bit, so this is my crafting the model file. As you can see, here's the key value stuff, then some heap shaping, then some ROP chain stuff. And I prepared it like this. I have a stripped down version of Ollama running on this server, and I prepared the input already to send it over there. I just send the model and it gets executed essentially. So you can see the model is loaded, and I already have the shell. We don't see it yet, but I can run ID or ls or whatever, and I can execute commands on the Ollama server. And actually, I turned all of this into a CTF challenge. So if anybody of you wants to give it a try based on what you saw today, and I will also release a blog post next week or in 2 weeks about it, you can have a go. It's still online, the challenge server. Not sure how long, but you can also run it offline and see if it works. So let's wrap things up. Looking back at the initial goal, I wanted to participate in Pwn2Own. As you can see, I only finished the exploit with Pi disabled, so it wouldn't have worked in the competition, so I didn't end up sending in a competition entry. But I was going to the conference anyway, where the competition happened, so I was now on the train to Pwn2Own, and I was like, okay, let me check if anybody else tried Ollama, because they released a schedule of which entry happens when, and nobody did it. So at this point, I was a little bit mad at myself and was like, I should have kept going. I should have tried it. Maybe it would have worked out. I would be the only one having an entry, and this would mean if my exploit succeeds, I would be the one winning the whole prize money and getting all the points. But I didn't, so no points and no money for me. But then I was like, okay, let me check if the bug is still there. Maybe they changed some of the code. Maybe they fixed the bug. So I go into the Ollama repository and I see a commit 1 day prior to me sitting in the train to the conference. And they say, update mllama to use Ollama engine. Okay. I look at the commit and I see a lot of removed code. Doesn't look too good. And the whole file was removed with the vulnerability in it. They just rewrote the whole thing in Go, which is a good thing from their end because it's much more safe now. I also checked. They don't have any vulnerabilities I could find there. But then I wasn't that mad at myself anymore because if I would have sent in an entry, it would have been patched 1 day before the competition. So I would have been probably even more frustrated if that happened. So turned out good in the end. All right, let's wrap up. First of all, don't do Pwn2Own. No, I'm kidding. Actually, Pwn2Own is quite a nice opportunity to learn and to look at things that you might not usually look at. So I actually do recommend participating in the competition. You can see, even if you don't find a successful exploit, you still learn a lot. And also you can make a CTF challenge out of it and make a talk. And yeah, I did learn a lot about a little bit more about binary exploitation, but also about Ollama and how large language models work on a lower level under the hood. And I also have a takeaway that is basically AI stuff has a lot of efficient and performant code, but that can a lot of times mean that it's also unsafe. If they write it in memory unsafe languages like C, C++, there's a lot of opportunity for things to go wrong. And I also feel like the velocity of how AI things are developed at the moment is more in a vibe of move fast, break things, and breaking things can, of course, mean that there's security vulnerabilities. Thanks.